So today we are going to study the implementations of the locks. So in the previous part of this lock-based concurrency, we saw the use cases of the locks and the interface of the locks. And in this part 3, we are going to actually look into the implementations and see why they are correct and then what properties they are actually satisfying. So recall that lock is used in order to use sequential data structures as if they are concurrent. So suppose that there is a vector, for example. A vector is one of the most representative sequential data structures. It is just an array of elements, and you can push an element to the end of the vector, etc. And the most easy way to make it concurrent is protecting this vector using a lock. So when a vector is paired with a lock, then you first need to acquire a lock before accessing the underlying vector. And after acquiring the lock, you can mutably access the vector. And after releasing a lock, then the other threads can acquire the lock and then access the vector. Locks are serializing all operations of the old threads, and therefore it is completely forbidding the concurrent operations. All the operations are serialized, and at the same time, only one thread is accessing the vector, for example. It is very important because lock is very important because majority of what is called concurrent programming is actually covered by these locks. So in most cases, concurrent programming is trying to utilize multiple resources that may share the same resources, but it is not particularly interested in optimizing or making it scalable for the high performance computing. In most cases, correct synchronization is the purpose. So for example, in the operating system, if a data structure, for example, a clock, is rarely accessed by multiple threads, then you can safely protect the clock using a lock. It may degrade the performance if multiple threads are trying to access the same clock at the same time, but our assumption is that it doesn't happen much. So it is sufficient in performance-wise, even performance-wise, it is sufficient to protect the clock with a lock. But if you are really trying to make your data structure scalable and you want to exploit the parallelism opportunity that is allowed by the program, you really need to use other methods. So because lock is completely forbidding concurrent operations, but in some cases you want to actually allow multiple threads to access the same data structure at the same time. So that is basically the trade-off of the lock. It is easy to use, but it is inscalable. Okay, and this repository contains the lock implementations, and you can see the safe API in Rust and the actual lock interfaces. I mean, actual lock implementations, including SpinLock, TickenLock, and this kind of locks. So we are going to deal with this kind of locks in the later stage of the lecture. And today we focus on the API here and the SpinLock and their implementation. And there are many kinds of locks, and these locks also have trade-offs. So one want to have a simple, fast, compact, scalable, fair, energy efficient, and all the good properties for a single lock. But unfortunately, multiple locks have different characteristics and they have fundamental trade-offs between them. For example, SpinLock is the most simple lock implementation, and it is quite fast when uncontended, but it is inscalable and it is not fair and it is usually not energy inefficient, etc. So you need to choose the right lock for the right workload. That is basically the reason why. The reason is that there is a fundamental trade-off multiple lock implementations. Okay, let me first look at the APIs and then the SpinLock. So we already discussed the API of lock in Rust. So you already saw the send and sync traits and the API that contains the lock and unlock methods and token, etc. But I'd like to recap the lock safe API in order to give a concrete context for a implementation of the SpinLock. Okay, so recall that a trait is a type class or a predicate of types. So a trait means that, oh, this type satisfies something, this type satisfies something, or this type doesn't satisfy these properties. So you want to express that idea. You want to express the idea that some of the old types satisfy some properties. In order to express that idea, you are going to use traits. Trait is expressing a predicate of types. For example, here's a send trait that is provided by the Rust standards library. And send means that if a type T is send, that means that the data T can be transferred to the other threads. For example, you can send an atomic use size that is meant to be a concurrently accessible word that can be sent to the other threads. Also, this use size is also sendable to the other threads. But probably, if you have a thread local storage, and then it should not be sent to the other threads because it will be specific to a certain thread. For example, by holding the thread ID, etc. And this storage, this resource cannot be used by the other threads. That's the reason why this kind of type should not implement the send. Okay, on the other end, there is a sync trait. That means that it is that if the type T implements the sync trait, that means that the type T can be concurrently accessible from multiple threads. So that means that, oh, I am thread A and you're thread B, and thread A and B can concurrently access the data. So for example, atomic use size, which is meant to be a concurrently accessible word, that is definitely a sync because it is the purpose of this type is allowing multiple threads to access it at the same time. But on the other hand, a simple word that is not meant to be concurrent, that is not sync, because you are not particularly marked the type as sync. Obviously, the thread local storage is also not sync because it is meant to be used by a single thread and it should not be accessed by the other threads. So that is basically the meaning of send and sync. And for more information, please go to the Rust documentation and read the descriptions there. And send and sync have a very interesting property. Here is that T is sync if and only if each reference type is sendable. That means that T can be concurrently accessible if and only if the reference type, the reference to T, is sendable to other threads. So it is this is very much the same property. So this obviously explains the meaning of this sync. The reference is sendable. That means that the type T is concurrently accessible. So please memorize what was written here because the send and sync trait will be used throughout this lecture, throughout this class. And if you are interested in implementing concurrent programs in Rust, then you're going to use this trait all the time. In addition to the two traits provided by the standard library, we are going to use another trait that is called row lock. Role lock means that it has API and that includes the lock and unlock function. We already discussed this interface, but I'd like to rephrase this. So it has a lock and unlock, and when you lock on a role lock, then you're going to get a token, and that token will be used to unlock the lock. And you have to guarantee that the token provided by a lock should be returned to the unlock function. That's the guarantee you have to make sure the satisfied. And this role lock is also data. For example, SpinLock contains a Boolean value or that indicates whether the lock is held or not. So it is also data. It is a resource and it contains information inside the lock type. So it needs to implement this trait as well. So to initialize the lock, you need to implement the default trait, which means that you can just create a new default value of role lock. So please go to see the documentation of the default trait that is defined in the standard library. That means the trait means that you can create any times you can create a default value of the type. Also, this role lock should be sendable and sync because this is a lock and this is meant to be accessible from multiple threads, and that's the reason why it should implement both send and sync. It should be sent to the other threads and it should be accessible by multiple threads at the same time. So this is defined in the repository, and please go read and the documentations and the implementation there. And this role lock has many assumptions. So in order to implement, for example, SpinLock and say that SpinLock implements the role lock trait, you need to guarantee a few properties of SpinLock. And one of that is that the things about token. The token is already discussed, but the most important property that you want to make sure for a SpinLock is that only one agent has acquired a lock at a time. So the purpose of the lock is mutual exclusion. No two agents are concurrently holding the lock at the same time. It is the fundamental property of the lock, and you have to make sure that it is guaranteed. So we are going to implement spin locks, ticket locks, and other kinds of locks that guarantees this mutual exclusion property. So only one agent acquires a lock at a time. No two agents are holding the lock at the same time. Okay, this is the API. API's descriptions. And using these three traits, send, sync, and roll up, we implement the lock types. So recall that with the lock, you want to guarantee two things in Rust. The first thing is that you want to associate a roll lock with the data. And the others is that you want to automatically release the lock when you finish accessing the underlying data. So these are the two structures that guarantee that. So first, this lock type has two components. L is the low lock and T is the data. And it owns the data T, and the object of type T is protected by the L lock. For example, L is a spin lock, then this is a T that is protected by a spin lock. If L is, for example, a ticket lock, then it is the T that is protected by a ticket lock, etc., etc. And this type guarantees that, again, that like the like the guarantee of the roll lock trait. Only one agent acquires the lock at a time. This lock type guarantees that the T object is not concurrently accessed at all. So only one agent is having an access to the underlying data that is guaranteed by these lock types. So recall that you want to associate the lock with the data, not the code region. So you should not think of safety of the concurrent programming in terms of code region. You should be able to think of the safety of concurrent programming in terms of data. Which resource or data is protected by which lock. So this mandates us to think in that way because we are explicitly associating a lock and a data. That's the reason why this API automatically guarantees the reasoning in such a way. So for example, we have this type. This is a lock. Lock protected data, and the lock is SpinLock, and the data is a vector of words. Or this is a lock protected data, and the lock is what is called CLH lock that we will learn later. And the protected data is a reference to some thread local storage. So in Rust, we can express that idea too. This is a very local. This data actually should not be sent to the other threads, but you can still protect the lock here, and you have to make sure that even though it is lock protected, because the underlying data is not send and seek, it cannot be accessed by the other threads. You have to make sure that, and that kind of constraint will be implemented by the lock guard and this trait constraints. So this lock type is sendable and sync if the type T, underlying type T, is sendable. So this type is not sendable, right? This is a TLS, and even there is a reference to the TLS, and you can immediately see that, oh, this type is not sendable because it is accessible to the thread local storage that cannot be accessed by the other threads. And that's the reason why this entire type, lock protected data of this TLS, it is not sendable and it is not sync because this lock type is defined as send and sync only if the underlying type T is sendable. So that actually means that a lock is meaningful. This lock protected data is meaningful only if the underlying type T is sendable. That's basically the idea of this constraint. And on the other end, in this type, in the left type, the vector is sendable. Even though you created a vector, you can safely send the vector to the other threads. So it is quite obvious from the API documentation. And that's the reason why T is sent for this case. And as a result, this lock type, lock protected data type, is also sendable and sync. Okay, that is the type constraints or trait constraints. And this kind of idea is implemented in Rust using some hacky way. And you please read the code and see what's going on there and how to express this idea in this lock type. Okay, so lock achieves its goal. It is associating a lock with the data. And the second construct, that is the lock guard, is achieving the second goal here. The second goal here is that you want to automatically release the lock when you no longer access the underlying data. So in order to do that, you define a new type, lock guard, which is basically an accessor to the underlying value. So it is a proof that you have acquired a lock. When you when you call an acquire for this lock type, then you are going to get the lock guard. That means that you acquire the lock and you are holding the lock, and it's meant to prove the lock is acquired. And it is RAII type, as we discussed in the previous lecture. It releases the lock when it is dropped. So it is automatically done. So if you are not going to intentionally forget about this lock guard, you are going to release the lock when the lock guard is dropped. And all objects must be dropped someday. So that's the reason why the underlying lock will be automatically released. So far so good, and it is very convenient. You don't need to track the lock, and you don't need to insert the unlock function for all the invocations of lock. So usually in C and C++, there are a lot of bugs related to this. You forgot about releasing the lock, so it happens all the time. And it also complicates the control flow of the program very much. And using RAI in C++ or Rust, the problem will be very much simplified. So this is much safer and easier API for using a SpinLock. And also this lock guard is dereferenceable mutably to the type T. That means it is a mutable accessor to type T. If you have a lock guard, then you can get a reference or mutable reference to the type T that references to the underlying value that is associated with the lock here. So if you have a lock guard, it can be transformed into a mutable reference to the type T. Okay, so that is very much expected because you are holding the lock, so you should be able to access the inner data. Okay, and furthermore, this lock guard is send if the underlying type T is send, and it is sync if the underlying type T is sync. In other words, this lock guard is transparent in terms of the send and sync traits. So let me say this way. So if T is sendable, then you can send the lock guard to the other threads. That means that you can acquire a lock and then transfer the knowledge or the ownership that you have acquired a lock to the other threads. And then the other threads can also access the data because it is implementing deref and deref mute. So that's the reason why you have to require the type T is sendable. Only if the type is sendable, you can safely send the lock guard to the other thread so that the other thread can safely access the underlying data. And the other threads, when passed by this lock guard, it can drop this lock guard and release the lock. So if this lock guard is sent to the other thread, it effectively means that the lock is acquired by a thread and then it is released by the other threads. It is possible because T is sent here. Also, if you have acquired a lock, then you can share the reference to the data to the other threads. So that's in order to do so, you have to make sure that T is sync. If T can be accessed by multiple threads, then the lock guard can also be accessed by multiple threads and deref to their own types. So that is basically the reason is that if T is not sync, then it is unsafe to share the lock guard because the other threads may dereference to the underlying data. So in order for the other threads to safely dereference the underlying data, the type T should be sync as well. And that basically the explanation I have so far is summarized like this. Lock guard is a transparent accessor with respect to the send and sync trait and list. Okay, And I have discussed many guarantees about the APIs, and these APIs and safety are actually proven, formally proven with respect to Rust ownership type system. So, so I can be quite sure that the the guarantees, as far as you satisfies the API's guarantee, then the underlying implementation will work as expected without any worrying about the bugs. So that is formally proven. That means that there is a proof and that is checked by the machine. So there is no way this proof can be wrong. So that's the power of the Rust as opposed to C and C++. Okay, this was about the Safe API in Rust, and we are now focusing on the implementation of the rule locks. So you want to implement a SpinLock, and then we have to make sure that the SpinLock satisfies the guarantees or the specifications of the rule locks. And we are going to start with the SpinLock. And the SpinLock is implemented in this file, and this is an excerpt from this file. So in order to look at the every detail of the implementation of the SpinLock, please visit this site and read the code. Okay, and here now let's look at the structs and the unlock and unlock function for a SpinLock. So we already briefly discussed the implementations, but I'd like to repeat in order to explain the orderings here. So we learned the orderings, acquire and release orderings. So here we want to reason about the safety of the SpinLock using the acquire release orderings on top of the promising semantics. Okay, a SpinLock is basically a Boolean value, and the Boolean value indicates whether the lock is locked or not. The true means the SpinLock is locked, and the false means that it is unlocked. And furthermore, this Boolean should be atomic because multiple threads are trying to acquire or release the lock at the same time. So it should be somehow sync. And in order to make a Boolean sync, you have to use this atomic Boolean type. Okay, so far so good. This is an atomic Boolean, and you are going to implement a lock function like this. So in order to acquire a lock, you want to make sure that before you acquire a lock, the lock was false. That means it is unlocked. And right after you acquire the lock, you have to make sure that the lock contains the true value because you just acquired the lock. That means that the lock function should atomically replace the false value with the true value. So that is the purpose of this compare and swap function. So compare and swap function is atomically replacing the value from false to true. So that's basically the purpose of this lock. Then if this compare and swap is successful, that means that you successfully replace the false value to true, then you know that you have acquired a lock. And then you can return from this lock function because you have acquired a lock. On the other hand, it may be possible that your compare and swap may fail because the value there is already true. And you cannot replace false to true because the value is not false at all. If that is the case, you have to loop again. You have to go to the beginning of the loop and try the compare and swap again. That's the reason why this is called a spin loop. It is spinning in the while loop, and it only if it successfully replaces the value from false to true, it will exit the loop and return from this function. Okay, so this is the lock function. And on the other hand, in unlock function, you are just storing the false value to the the underlying value here. So you know that you already acquired a lock. So you know that the inner value is true already. And you also know that you are the only one that who knows the value is true, because you acquired a lock, and that means that the others doesn't hold a lock at all. And that's the reason why you can just store the false value. You don't need to replace the true to false value, because you already know that the value is true. You can just store the false value to the value, the inner variable. And this store can help the other threads to acquire the lock, because they are waiting for the value to be false, and false is replaced with true. And after this thread is storing the false value to the inner variable, then the other threads can replace the false value to true. And this is the reason why this can be implemented as a store. Unlock function can be implemented as store false. Okay, so far so good. And the syntax is a little bit different from this code here, because in order to make it into a one slide, I made a very much simplification. But please visit this site and see what's going on there. It contains the complete implementation that is in valid Rust. Also, you can notice that there is an acquire and release orderings. And you may wonder, what's the meaning of this? Why you need this? So, because already mutual exclusion seems achieved, because it is atomically replacing false to true. So there is no way that multiple threads are holding the locks at the same time, and you can store the false value because you definitely know that you have acquired a lock. And why are these orderings, acquire and release orderings, are even necessary? What is the purpose of this? So I'm going to explain the necessity of these orderings in the next slide. Okay, this is the shorthand notation for the previous slide, and I'm going to explain what's going on in the promising semantics when the lock is held and unheld. So lock is meant to be protecting data. So I'd like to show you how data will evolve and how data will be protected by the lock using this implementation. So suppose that this bright green thread, let's say this is thread 1, and the dark green thread, let's say this is thread 2, are trying to acquire a lock. So lock is false at the beginning, and let's say that the lock is this message knows the latest value of this data. So it has a view, it has a release view, and its view is pointing to the latest value of D. So suppose that D is also data, and some values are written to this location D, and at the end of the access to the D, the lock should be false, and these false messages release view should point to the latest value of this D. And suppose that thread 1 has acquired a lock. And recall that in order to succeed in this compare and swap, you have to put an adjacent message to the previous value. And it was false, and it is now true because you are compare and swapping the false to true. So that's the reason why we put the T message here right after this F message, because they should be adjacent. Okay, so far so good. So, and the purpose of the lock is that the T1 should be able to access the latest value of D. Or in other words, this T1 should not access the stale value of D. And as a result, the T1's view should be updated to point to the latest value of D. And that's the reason why it should be acquired. In order to always observe the latest value of the location D, you have to acquire the compare and swap. And when this is acquired, you are going to acquire the release view of the previous message that is meant to be pointing to the latest value of this D. And it should be acquired by this lock function. Now, after T1 has acquired the lock, T2 may want to acquire the lock, but it will fail because it cannot replace the false value to true, because the only false value here is already appended by a true message, and this T message cannot be cast because it requires the previous value to be false. And that means that T2 cannot succeed in compare and swapping the value, and it will always go to the error branch and loop again and again. So until T1 finishes the accesses and unacquires or releases the lock. Okay, now T1 has acquired the lock and it is fine, and it will be able to access the data T, and it will even modify the data as it wishes because it is provided by the lock API. You acquire the lock, so you can arbitrarily modify the data D. And suppose that the view has been updated to this, and this contains the latest value of D at this point of time. And now T1 is trying to unlock the lock so that T2 can acquire the lock later. So recall that the inner value is stored with false. So you're going to, oh, I'm sorry. I'd like to first explain the T2 case here. T2 is also trying to call a lock, but it fails to cast. It just reads that the latest value is true. So you know that, oh, inner is true, so I cannot succeed in cast. So you are going to go to the error. And because it is acquired, you know you acquire the view here because this is released by this message. But you're not going to acquire the lock. So you have to spin here, basically. You cannot acquire the lock and spin here by reading this message again and again and again. Now, T1 unlocks the lock. So recall that you store the false value to the inner value. So you create a new message that contains the false value. But at this point of time, you are going to release here. So this is meant to be guaranteeing the invariant of the false messages. False messages should point to the latest value of the location D. And that's the reason why you are releasing it. So before that, its view is pointing to D. But in order to transfer the knowledge here, the knowledge that you have already acquired this view, and the latest value of D is here, and in order to transfer the view here, you need to release the view to the message. That's the reason why this released messages view points to the latest value of D here. And also that's the reason why it should be released. The view on D should be released here. And after that, in the same way, T2 can acquire the lock, in this case by appending to the false message, and also this view is acquired. And as a result, T2 also can see the latest value, because the latest value here, and it is released by the T1 to this message, and this message's view is also acquired by T2. And T2, it should observe the latest value of this D. It cannot read or write to the previous area here. So that's basically the purpose of this release and acquire synchronization. So to summarize, all the information that is modified is T1 should be released here to the message. And on the other hand, the message's view or information should be acquired by the next successful lock invocation. And as a result, all the accesses by T1 is ordered before the T2's operation here. And as a result, there should be no concurrent operations among this T1 and T2. And that is guaranteed by this release acquire synchronization from unlock to the message to the lock function. So this is basically the meaning of the second line. Events between lock and unlock function are transferred via release acquire synchronization. Okay, and T2 can access the value D, and it may update the view, and later it can unlock its lock with the latest value of D here. So this message also contains the latest message of the D here. It is invariant. When holding the lock, you'll access the latest value of D, and also the false message is holding the latest value at that time. So that is basically the reason why lock and unlock satisfies the guarantee, the mutual exclusion, and the fact is explained in this promising semantics using this diagram. Okay, so far we discussed we revisited the LockSafe API in Rust and looked at the SpinLock's implementation and what's going on in the execution of the SpinLock implementations on top of this promising semantics. So in this promising semantics, you can reason about the safety and the guarantee of the SpinLocks in this way. So T1's accesses during here are strictly ordered before T2's accesses here, thanks to the release acquired synchronization from the unlock to this message to the acquire